This presentation is a topic review of droplet generation by Jordan Dai, Mohammed Haider, and Vishal Thakur. Here's our agenda for today.
Microfluidics has various areas of research that are being studied. Our area of interest will be droplet formation. To form a droplet from a continuous liquid phase, energy needs to be introduced to the droplet surface so that some of the energy is converted into surface energy. This confined space in the microchannel increases the resistance against the flow of the continuous phase. Thus, it produces an increase in pressure drop upstream, which constricts the interface until the droplet becomes too narrow and breaks away from the flow.
Droplet generation requires two immiscible fluids. The two phases are called the dispersed phase, which can consist of oil, alginate, or fibrin, among other things, and the continuous phase, which can be oil or anything else immiscible. The droplets are the dispersed phase, and they are moved along the main channel by the continuous phase. The figures on this slide detail how the dispersed phase moves along the main channel.
Moving on to control of droplet formation, there are several factors that contribute to droplet formation. Flow rates of both dispersed and continuous phases are one such factor that can contribute to variation in droplet formation sizes. Additionally, fluid properties such as viscosity, fluid density, etc. can also influence droplet formation attributes. Another factor that can control droplet formation is the interfacial tension that occurs between the two phases. Interfacial tension is the tendency of the interface to become spherical, that is, attain the lowest surface energy possible. This phenomenon is due to an imbalance of intermolecular forces between the two phases. Yet another contributor that can control droplet formation is channel geometry. In droplet-based microfluidics, channel geometries comprise of cross-flow geometry, co-flow geometry, and flow-focusing geometry. Cross-flow geometry can be a T-junction or Y-junction geometry as seen in the top left and top right images respectively. Cross-flow geometry is a passive formation method that forms uniform, regular-sized droplets and is typically utilized in droplet microfluidic devices. Co-flow geometry is also a passive formation method and is seen in the middle right image. Both phases are flowed together, which contributes to formation of varied droplet sizes, that is, polydispersed droplets. Flow focusing is another passive formation method which is seen at the bottom right image. This formation method forms smaller sized droplets due to constrained narrowing of channels. As seen from the previous slide, there are passive droplet formation methods and also active droplet formation methods. Active droplet formation methods utilize external energy in forming of the microdroplets. Some methods of initiating the process is by electric, magnetic, acoustic energies, centrifugal forces to name a few. Contrarily, passive droplet formation methods do not use external energy and are largely seen in simpler device designs. Droplet microfluidics relies on many complex mathematical principles. However, a simple yet significant one is the Reynolds number. The Reynolds number is a dimensionless number and is characterized by the formula on the right. Reynolds number below 2000 suggests laminar flow and above 4000 suggests turbulent flow. In droplet microfluidics, flow is characterized as laminar flow. Here are the advantages of droplet microfluidics.
These are some of the applications of droplet generation. Processes such as drug screening, virus detection, and food processing can utilize this technology. Drug screening is one specific application of droplet generation. The process can be seen in the figure in the bottom right-hand corner of this slide. Droplets containing a drug are trapped in the center of these channels. Once they're trapped, the droplets can be evaluated and the drugs can be screened. When done, the droplets are carried out of the channels by increasing the pressure, which forces the droplets out. Another application of this technology is using droplets to contain the synthesis of gold nanoparticles. Tetrachloroaurate, along with a photoinitiator and polyvinyl pyrrolidine, were coalesced into a droplet and sent through a beam of UV light. The nucleation of the gold particles was initiated by the UV exposure. The particles were then sent through a residence loop to finish growing. The size of the resulting particles was a function of flow rates of the reactants and UV exposure time. The fact that this process occurred inside droplets meant reactions could be better controlled.
Microfluidic devices show great flexibility in preparing shape-controlled microdroplets having unique chemical compositions thanks to the excellent handling performance, special laminar flow, and interfacial characteristics of microfluidics. This technology makes it possible to synthesize microparticles with specific structural morphology and functional properties. Droplet-based microfluidic technology exhibits great application prospects in the field of functional material synthesis, biomedical engineering, and food processing, to name a few. In bioprocessing research, an application of droplet could be used to cultivate even mammalian cells, for example as spheroids or tissue fragments.
Here's a list of references. Thanks for watching.